Hi everyone, so you've survived quantum numbers, you've survived looking at orbitals, now we will start writing something called an electron configuration. So the bad news is it's unlike anything you've ever seen. The good news is, the great news is, it's based off of those quantum numbers and those orbitals, and once we get the hang of it, it's very straightforward, it's very organized, it comes right off of the periodic table. So we're going to be taking a look at the periodic table today in a second. But first, why do we do this? What are we doing electron configurations for? Well, we're basically trying to show where the electrons exist in an atom. What orbitals are they in? Are they in the 1s orbital? Are they in the 2s orbital? Where would we find them? Essentially, we're writing the address for a given set of electrons. This also helps us to determine how atoms will react and what sort of ions they will form. So there are three principles that we need to be aware of. They're named after we kind of thought about them. So first off, the off-ball principle. The off-ball principle states that electrons, they're going to start at the bottom. So imagine that we're moving into an apartment building. Everyone's going to jump on the lowest floors first. They don't want to move those couches up multiple flights of stairs. So the off-ball principle dictates that electrons are going to go to the lowest energy levels possible first. The Pauli exclusion principle says that if you're in a given orbital, so if I drew an orbital like this, electrons have to have opposite spins. So that means that one electron is going to point up while the other points down. And the convention, so you can save time, is to draw half arrows. So there's one up, there's one down. You may not have this. That is no good, no dice. Finally, Hund's rule says that if we are filling up a given set of orbitals, so for instance, let's imagine that this represents the 2p orbitals. So remember, 2p orbitals have three different orientations. That's why I've drawn three in here. We could get really fancy and number these as -1, 0, and 1, right? We know that that's the different combinations we can have. That's that m sub l. But what this says, Hund's rule says, is that as we go to fill those orbitals, we can't do this. We can't put two people in the same orbital before we do this. We first will put one electron in every orbital, and then we will come back and start pairing up. So let's do that again. The following is incorrect. We would not do this, right? What we would do is put one electron in every one of these orbitals and then come back and fill up. And so one way of thinking about this is if you have siblings, right? So let's imagine that you have a bedroom or a house that has 3 bedrooms for the kids. Mom and dad have their own bedroom, but there are 3 bedrooms left for the kids. And let's imagine that you are sibling number 1. Here you are. There's no way, if you have a baby brother or sister come along, that you want them moving in with you, right? Heck no. They're going to have to take their own spot in another room. And if another kid comes along down the line, then they're also not going to want, your new sibling's not going to want to stay with anyone else, so they're going to take their own room until we reach a point where we have to start doubling up, right? We don't have enough rooms for anyone. Then and only then do we start adding these extra electrons into these unfilled orbitals. So Hund's rule says one at a time. Let's do it one more time. We're going to go one at a time through the orbitals. Convention is left to right, like so, until we get to the end, and then we're going to start filling up like so. All right, so orbitals also fill, as we saw there whenever we were looking at the off-ball principle. They kind of start at the lowest energy and work their way up. So electrons are going to start in the 1s level, then 2s, 2s, then 2p, then 3s, etc., 3p, 4s. Then what the heck is going on here? We all of a sudden go from 4 to 3 and back to 4. Okay, so that is really weird, and to help describe that, we need to look to the periodic table. So if you don't have a periodic table in front of you, go grab one, take it out so you can join me on it. It's going to really be valuable to you. Pause the video, whatever you need to do. Hopefully you have yourself a periodic table. Let's first do this. Let's number our periodic table with energy levels. So over here, we'll do this in black. My n value, remember n is energy level, this is the first energy level, second, third, fourth, fifth, sixth, and seventh. And remember that just goes along like so. So for instance, these elements are in the second energy level the whole way across. Okay. So when we write electron configurations, we read the periodic table like a book. We go left to right, we go top of the page to the bottom of the page, and we basically follow atomic numbers. So here's an atomic number 1, here's an atomic number 2. We are going to write the electron configuration or the code for the elements as we go in order. So from hydrogen to helium, and then we come over here 3, 4, 5, 6, 7, 8, 9, 10, and then we come back over here 11, 12, etc. And once you get to argon, you jump down here to number 4 and look what happens here. All of a sudden, we go into a new group. We go over here, right? So let's get to that in a second. Before we do, we need to define some areas on our periodic table. So first off, everything over here on the left, I'm going to outline this in red. This section that I'm kind of highlighting in red, and we'll fill it in just for our OCD. This section we are going to call the S section. If you remember back, S, it has one shape, right? So S can only have spherical orbitals. It's only number 0. It can only hold a grand total of 2 electrons. Actually, let me keep that in red. It can only hold a grand total of 2 electrons. And check it out. This thing is 2 columns wide. 2 electrons, 2 columns wide. That is not by mistake, not an accident. Just so you know, helium actually is part of the red section. Strangely enough, it kind of belongs over there as well. Okay, after S, this section that we will make green, and let me highlight this in green. Green is our P section. So the P section we're highlighting in green. Again, I'm filling in. You can do the same in color code if you so desire. So that is the P section. Remember that P has numbers. It has numbers -1, 0, and 1. Therefore, if every one of those can hold 2 electrons, we have a grand total of 6 electrons. And I'm again going to keep this green. We have a grand total of 6 electrons. And, check it out, how many columns do you see? 1, 2, 3, 4, 5, 6 columns. So again, no surprise. Let's go blue. Let's find our D area. So this section in the middle is the D sublevel. It's the D sublevel. D sublevel, if you'll remember, has numbers -2, -1, 0, 1, and 2. If you need to refresh your memory with the orbitals or the quantum numbers note guides, feel free, but you should remember those 5 numbers, which means if we have 5 orbitals, 2 electrons apiece, we can hold 10 electrons. And check it out. How many columns do you have? Well, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then finally, you might predict what's coming next. Down here on the bottom is the F sublevel. And the F sublevel, remember, has 7 numbers associated with it. It can go from -3 to -2 all the way through 0 and then back up to the number 3. That has 7 numbers, which means we can hold 14 electrons, 2 electrons per orbital. And if you look at this, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 columns. So all is well. Now, we are going to write electron configurations for given elements. The best way to do this is simply taking an example out of your note guide, right? So on your note guide, you have to write the electron configuration for sulfur. So I'm going to do this with us right up in this space right here. I'm going to write the electron configuration, but if you want to write it on your note guide, feel free. So sulfur is going to take us on the following journey. We are going to go from the top of the page. We're going to read it like a book. We're going to start with number 1. We're then going to make our way over to number 2. Then we're going to go 3, 4, 5, 6, 7, 8, 9, 10. After 10, we jump down here to 11, 12, 13, 14, 15, 16, and we are going to stop right there at sulfur. So if we go on that journey, we are simply going to write out the code for everything that we go through with one little caveat. You write the code for a final sublevel instead of every single atom. So here's what I mean. The first thing that we see, the first thing on the periodic table is hydrogen, right? Hydrogen is in the first energy level, so we would write a 1 for that. It's in the S sublevel because it's red, and it's the first element, so we'd write 1s1. Then we'd go on over to helium, right? Helium is in the first energy level, it's at the top. It's in the S sublevel, it's red, and it's the second element, so that would be 1s2. Energy level is a whole number, S is a lowercase letter, and then the number of the electron is a superscript. After that, find number 3. Number 3 is here, it's lithium. Lithium is in the second energy level, S sublevel, element 1. Then beryllium, second energy level, S sublevel, second element. After beryllium, number 4, we have to come on over to boron, number 5, right? So that is in the second energy level, P sublevel, element 1. Carbon is 2p2. Nitrogen is 2p3. Oxygen is 2p4, 2p5, and all the way over to neon is 2p6. And you can see really quickly that this is going to get really, really annoying, right? There are so many different letters and numbers to write in. So, good news. We can have a little bit of a shortcut. First off, every time you fill a sublevel, so remember here, S can only hold 2 electrons. We've filled that sublevel. You only write the code for the last element in the sublevel. So instead of writing 1s1, 1s2, we're simply going to write 1s2. Same thing here. We have a full sublevel. So instead of writing all of that out, we're simply going to write 2s2. You'll notice over here, P can hold 6 electrons, so we have finished an entire sublevel. Instead of writing out this entire thing, we're simply going to write the last part, which is 2p6. We're not done yet, though, because 2p6 took us over to neon right here. That's 2. Remember, second energy level. P is green, and then it's the 6th element. So we still have more to do. After that, we come down to this sublevel. So that is the 3rd energy level, S sublevel. There are 2 elements. And then finally, we make our way over here to where sulfur is. Sulfur is in the 3rd energy level. It's in the P sublevel, it's green, and it's the 1, 2, 3, 4th element in. So it is 3p4. So our final electron configuration for sulfur is this. It is 1s2, 2s2, 2p6, 3s2, 3p4. And little pro tip here, one little fun thing, add your superscripts together. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 4 is 16. Sulfur has 16 positive protons, which means it must have 16 negative electrons. So the fact that those numbers match up is not a surprise, and it's a great way for us to check our work. So what's the point? Why are we doing this? Well, this code, this allows chemists to figure out where the electrons are in this atom. So we would say around this nucleus in the sulfur atom, there are 2 electrons sitting in the 1s orbital. There are 2 electrons in the 2s orbital. There are 6 electrons occupying the 2p orbitals. There are 2 in the 3s orbital, and there are 4 electrons in the 3p orbitals. So it allows us to kind of make a roadmap or a key to some extent for where our electrons are located. Let's try one more together. I'm going to try to erase some things without messing a whole lot up. So let's erase this. We can erase these things. Again, if you want to do this on your note guide, that might be the easiest way to do things. All right, we still have a semblance of our periodic table left here. So next up, we're going to gallium. And gallium is letter Ga. It's down here, number 31. So let's follow through. Again, let's read like a book. We'll start here with hydrogen. We start off with 1s2. As you follow along on your periodic table, you'll notice the next place you get to is lithium, so that's 2s2. And then you get over to boron, and boron is on the second energy level. It's in the P, so it is 2p, and there are 6 elements, so that becomes 2p6. And then we come down here to sodium, and sodium is in the 3s, and there are 2 elements, so that's 3s2. And after that, we get over to aluminum. Aluminum is in the 3p, and there are 6 elements, so that is 3p6. And after that, 3p6, right, this is the third energy level, P sublevel, 6 atoms. After that took us to argon, number 18. After 18 comes 19. So this is 4. We're in the S sublevel. There are 2 elements. So this is 4p2, 4s2. And then, let's pause. After 19 and 20 comes 21. So we're now in the D sublevel. But there's something really interesting that happens, right? Because, remember this progression. In the first energy level, there are only S sublevels. In the second energy level, there are S and P sublevels. S and P. Geez, technology issues, my apologies. S and P. I'm going to write this in a new location because this thing doesn't like me. So, in the first energy level, there are S orbitals. Second energy level, there are S and P sublevels. Third energy level, there are SP, and this is where the D has to come in, right? So the D sublevel has to originate in the third energy level. We saw that earlier based on the M sub L quantum number. And similarly, the fourth energy level is where the F sublevel has to come in, which means on the periodic table, things are a little bit weird, right? So after 4s, we actually go to D, but this is the first place where we see a D sublevel. This must be 3D. So it turns out for the D sublevel, the energy level is actually 1 less. That means the 3D sublevel is sitting in the 4th energy level. 4D is sitting in the 5th energy level. Similarly, 5D is sitting in the 6th energy level. And just when you thought that was kind of okay, but still confusing, look what happens with F. So F, you'll notice where these numbers actually sit. 58 belongs right here after 57. 90 belongs right here after 89. So really this whole purple section belongs right here. It belongs up in this area, which means that if this is our F sublevel, and F has to start in the 4th energy level, then this is 4F, and this is 5F. So you actually have to subtract 2. 4F happens in the 6th energy level. 5F happens in the 7th energy level. So for F, you actually subtract off 2. For D, we subtract 1 from the energy level. For F, we subtract 2. But I digress. So we now know that this, number 21, this is 3D. So there are 10 elements in the D sublevel. We're going through all of them. So then we go to 3D10. And then finally, we're trying to end at gallium. Gallium is in, remember, this is 4p. S and P are correct with their energy levels. So this is 4p1. So our final electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. If you want to add your superscripts together, you will find that you equal 31. Now let's also back up really quickly to this page where we were before, and notice, I kind of glossed over this earlier, but check it out. It turns out that 4s, Notability wants me to rate it. We'll come back to that. It turns out that 4s happens after 3p as expected, but then we go to 3d. So check it out. The energy that we saw here actually predicted what we saw. We go from 4s to 3d to 4p. Okay, let's continue on. Pardon me. Let's try another one. we are going to try hafnium. If you want to pause the video and try it yourself, feel absolutely free to do that. Hafnium is HF. So take a second to find it, and you'll find it right here, number 72. So here is hafnium. All right. Let's get there. Let's do an electron configuration. I'm going to go a little bit faster. Again, you can pause. You can come back and get here and try it yourself if you'd like. So to get to hafnium, you should have followed through the following elements. You should go hydrogen and helium, so 1s2. Then you'll go to 2s2, 2p6, 3s2, 3p6, 4s2. After 4s2, you kind of see where that is, right? 4s2 is in the 4th energy level, S sublevel second element, that takes us to calcium. Now we go here, this is the 3D sublevel. So after 4s2, we go 3d10. Just like gallium before, we then pop out back into the 4p sublevel. So after 3d10 is 4p6, 5s2, 4d10, right? 4d10 is right here. Here's 4d, we went through all 10. Then we're back up to 5p6, then 6s2, and then depending on the textbook you're using, you may see some weird things happen here, but 6s2 took us to right here. Depending on your table, periodic table, some people will go into 5d1, because this is number 57, lanthium. Others will go directly into 4f14. We are going to do the second one because it makes a little bit more sense. So this periodic table isn't ideal for electron configurations, but you'll see it written two different ways. So after 56, we're going to jump right down here. We're going to go into the 4f sublevel. There are 14 elements. So we're going to go 6s2, 4f14, and then we're going to come back to 5d. So here we are in 5d, and hafnium is the second element. So that means our final thing is 5d2. And there's your final electron configuration. Again, you can add up all of your superscripts, and you will find that it equals hafnium's atomic number, which is 72. All right, one more for you to try. It's radium. Radium is Ra. It's a little bit crazier. We'll do this in a different color. Radium is right here, number 88. So let's try this together, or if you want to pause and go on your own, feel free, but here's where you should be. As you follow along your periodic table, you should go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 4s2 is the place where we first see the D sublevel, so we'll go 3d10. We'll go back to 4p6, 5s2, 4d10, 5p6, 6s2, and after 6s2, you'll notice that we find ourselves right here at barium again. So we said after 6s2, we go to 4f, down to 4f. There are 14 elements, so after that we have 4f14, and after 4f14, look at 4f14 ends at 71, so we then come back up to 72, but we did a weird little jaunt with our periodic table, so we actually have to go here and go through all 10 of these 5Ds. So we go from 4f14 to 5d10. What happens after 5d10? Well, after 5d10, you're up to this element, thallium, so we're now back up to 6p, right? Remember, S and P sit in the actual energy level where they are. So now we're up to 6p6, and finally, after 6p6, 6p6 takes us all the way to radon. We are down to number 87 and 88. We are into 7s, and radium is the second element, so 7s2. And that is your full electron configuration for radium. And if you're noticing that the beginning parts of these electron configurations, for instance, all of this is the same as all of that, You're absolutely right. We will take a shortcut in the next video.